Welcome to today's webinar on Marc 2013.1 release overview. My name is Srinivas Reddy, and I'm a product marketing manager at MSC. And today's presenter is Dr. Ted Wertheimer, who is the director of product management at MSC. So in today's presentation, he is going to go over the new functionality introduced in this latest release of Marc. And if you have any questions during the presentation, please post them in the Q&A panel, and we will get to them once the presentation is done. And with that, I would like to turn the control over to Ted.
It's a pleasure for me to talk to you about the new release of the Marc product, Marc 2013.1. As many of you know, in calendar year 2013, we've had two releases of the product, and this is the second one, and it really effectively focuses on four areas: improving the ease of use of the product, as we will see in the following slides. Of course, we always focus on the area of contact. And here the area has to do with a option having to do with initial gaps in the model, or sometimes called the clearance option, and material trimming. The third item really is in the area of fracture and durability. Of course, many of you know in 2013 release, we first provided the capability of doing 3D fracture mechanics with adaptive meshing for crack propagation. And finally, the last area is in the area of new models, particularly for the rubber industry and the plastics industry. Part of ease of use really involves both in terms of setting up your model, and it includes improving the performance of the product. There was a lot of focus in the 2013.1 release to better utilize modern multi-core architectures of computer chips so that we can parallelize both the elements assembly time and the stress recovery time, which is often a dominant portion of nonlinear analysis. So this complements the other types of parallelization that we have in Marc, which is either using the domain decomposition method or using the parallel solvers, whether or not it's the Paradiso solver or the MUMP solver or even the multifrontal solver. So it's designed for large models, but it can be effective also in moderate-sized models, which are assembly dependent. So a couple of facts: it's only really designed for shared memory parallel type architectures. It can be used in conjunction with domain decomposition for distributed memory parallelization, where you use domain decomposition to parallelize in big chunks, and then you use this technique to parallelize the element assembly and the stress recovery for the within each domain. One of the nice things about this capability is it can be used with almost everything that's in Marc, and most importantly, it can be used in conjunction with global adaptive meshing to parallelize those two portions. So I have a couple of slides showing the results on some typical problems. The one problem is an aircraft panel. This is a moderately sized model, close to 600,000 degrees of freedom and 100,000 elements. If you have these types of aerospace structures, especially if you have a large number of layers in your shell elements, if you're using progressive failure, the element assembly time and the stress recovery time starts to dominate. And this analysis was done on a machine with Intel chip, 2 chips, each chip having 6 cores, so 12 cores altogether. We usually like to leave a few cores for the operating system, but you can see in such a model that using 10 of the 12 cores, effectively one gets a speed up of the element loops, meaning the assembly and the stress recovery loop, of close to a factor of 10. And what this does for you in terms of the total job performance, which of course involves other things like reading the input and the output, it gets you a scalability factor of about 4.5. So it's a dramatic improvement, and what it means is that we are really better utilizing the hardware of a modern computer. And a problem like an engine block, much larger model, 2 million elements, close to 10 million degrees of freedom. Again, what we see here, running it up to 8 processors, we see that effectively the elements assembly time and the stress recovery time goes down by close to a factor of, a little bit over a factor of 5. And the total solution time, which is now very much dominated by the decomposition of the matrix, goes down by a factor closer to 4.5. So very good performance. And what this really means is it means really 3 things. A, you can use your conventional problems and get greater throughput in your solution time. Or what you can do is you can use this improvement to basically refine your model even more to get greater accuracy for the same amount of wall time. Or what you can do is you can simply perform more simulations in that amount of wall time to get a better design analysis. The second big area of the 2013.1 release is we've introduced a model browser, what people in the CAD industry use, or what some people call as a navigator, that really gives you a graphical representation of your complete model. We'll do a little demonstration of this later. It allows you to easily pop between different menus, and it allows you to filter the model a little bit more. So this is a popular model. It's in the user's guide. I should note that the Marc user's guide has been substantially updated with the 2013.1 release. I'd say 90+% of the manuals are new graphics representing the new look and feel of the Mentat product. So what one observes is we have the model navigator over on the left-hand side. At least by default, it's on the left-hand side. And what it shows is it really shows your main menu buttons, but now it shows all the content of the main menu buttons. So this problem, which involves the gasket between these 2 different parts, has a lot of different tables to represent the gasket, has different materials, etc. in the model. And one can use traditional symbols of the plus and the minus to either collapse the menu tree, and you can basically, on a single click, you can open up everything, or you can close all the menus as well. To help you view the model, all the entities in your model are color-coded with the same colors that we use to associate with the identify, so one can quickly associate what's in the menu tree with what you see on the screen. And so it also means you could effectively hide this particular area and see the model over here as well. So that improves the visibility. The right mouse button allows you to click through the menus, and you can, again, all these are designed really so that you minimize the amount of mouse movement, that you can focus your eye really on one part of the menu and that you can more quickly navigate your model. So you can quickly turn on identify on or off, or edit the model, or introduce, of course, new entities into that model, whether or not they're new boundary conditions or new materials or whatever. And again, we see that these colors are nicely coordinated. Of course, the model browser is a capability that is only available in the new version of MenCat. In MenCat Classic, the model browser is not available, and we've done other things to enhance the graphic speed of the new MenCat, and we're really enthusiastic about the fact that more and more people are utilizing the new version of MenCat. Again, to show within the boundary conditions, if one continues to click over, you can basically edit an item, you can add a new item. Again, in all the menus that you would have seen up here, you can still get to as well. It should be noted that you can hide these menus as well, in which case you have a larger graphics area to see your model. You can also take the model tree, and of course you can dock it on another screen if you have a dual screen system, and we'll see that a little bit later. Using this procedure, the menus that are used to really define the guts of the code are slightly different. They're now effectively all pop-up type menus, so that when you say properties or add a new entity, you'll get a pop-up menu. Again, you can move this to the side and recapture the greater amount of graphics area. This is really, again, is going the same. It's in this case in the area of applying the details of your property action. So there are multiple different modes in using the browser. The default is the model navigator mode and the model mode, and that brings up the model browser. If you want to stay in your more familiar version that was similar to MenCat 2013, then one would have clicked on the dynamic menu model, in which case you would not see the model navigator. Similarly, there are two different modes up here. The model mode really shows it in this form, and we'll get to the list mode in a second. So the list mode, what it allows you to do is it allows you to filter what you see in the model navigator. So you could say, I just want to look at the boundary conditions, and then you could say, I just want to look at the boundary conditions with the letter P, and then what it would do is it would have filtered out all these other ones, and you would have only seen the boundary conditions that begin with the letter P. So if you have a very large model and you associate your names of different entities in a rational way, this is beneficial as well. Okay, the next really critical thing that's been added in Marc /MenCat 2013.1 is some enhancements to the geometry and meshing. So for the last about 18 years, we have used the ASIS solid modeling kernel for geometry manipulation in MenCat when we were using solids. This has now been replaced with the Parasolid geometry engine. This was done for several reasons. The first is that the Parasolid model technique is more popular in the CAD industry. There are more organizations that are using this, and so it allows us better compatibility. The second is the other MSC products, Patran product, SimX product, even Atoms all effectively use Parasolid as the engine. So this allows us better compatibility with the other MSC products. The good news is it not only is better solid modeling, but it also allows us to utilize other meshing technologies that are in the MSC products, including one-button meshing. So with the one-button meshing technique, we don't need to repair our surfaces. We don't need to introduce seed points. We don't need to match curves. And so with a single click of the button, we can get a geometry meshed for us. Of course, all the existing meshing techniques exist today as well. So a little example, creating a geometry, the exactly same solid operations menu exists, the same solid adding or removing bodies geometries exist. The one difference is colors are different. The color is actually more consistent with our coloring scheme for elements. All the solids will appear in the same color. Here I created a solid, I created a cylinder, I then did a subtraction, then I did a blending operation to generate this nice little fillet. I would then go into my meshing. I click volume meshing. The default is now meshing based upon the solid. I could either compute a good element size, or I could specify my particular element size that I wanted, and I would click Tet Mesh, and it would mesh the solid. So if I would just have said Tet Mesh, it would have automatically computed an element size, and it would have meshed the body. This mesher also has the capability to either generate linear elements or quadratic elements automatically. So if you want higher order elements, before you would have generated lower order elements, then you would have done a change class, and it would have used the attach information to get the correct curvature. Now this is again done just in one button meshing. So we're continuously adding more capability in MenTat for meshing technology, and this is a big step in 2013.1, and you will see additional new meshing technology in subsequent releases. So this was the mesh that was being generated for this simple problem, but of course we want to do more than just simple problems, so I'll demonstrate this later. This was our Parasolid engine model. This is in wireframe mode, then of course in solid mode, using the technology in MenTat that existed in previous releases. This would have been virtually impossible to do. You would have had to convert all this into surfaces, then you would have had to add these seed points, then you would have had to match the seed points, and it would have taken forever. Now we'll see that you can, depending on whether or not you use the default geometry distance, meshing distance, or select your own, you can easily generate a mesh. If you use the higher order elements and you do a get rid of the outlines, of course, you really see it's a very nice mesh, and it really captures the curvature of the model. This was a part that we gave the beta webinar, and somebody was so enthusiastic, he basically said, I've got a part that took me forever to mesh before. This part then meshed for him the first time in just a matter of a couple of minutes. Very complex part, very nice representations of the geometry in the model. Of course, we're always adding and enriching the nonlinear technology that exists in Marc. We've added a couple of new material models. The first one I want to talk about is anisotropic rubber. This is typically used in rubber belts. It's also used in rubber tubes. It's also used for biological materials, where effectively, whether or not it's the tendons that are in our own muscles or some sort of wires that are used to strengthen the rubber material. So we've introduced 3 different models that represent anisotropic hyperelastic materials. And in this little example, we use the Gasser model. In the Gasser model, you give really what is the distribution or the dispersion of the fiber directions, and then you can see what it's done here compared to taking a traditional isotropic rubber model. We have a much more focal distribution of the displacements and, of course, the stresses as well. In Marc 2013, we introduced frequency-dependent damping in a user-friendly manner and much more rich models. We've continued to enhance this in the 2013.1 release, expanding this for also orthotropic materials so that it can now be used in conjunction with composites, where one would effectively see different characteristics in the different preferred directions based upon the material properties. We also introduced a new shift function for viscoelastic materials, traditionally, again, either rubber-like materials or plastic materials. And this is the Arrhenius shift function, which is an exponential function to allow us to define this shift behavior. The advantage of the Arrhenius shift model is that it's very physics-oriented. One simply uses the ratio of the activation energy to the universal gas constant and the glass transition temperature, which are, generally speaking, physically known properties to represent this particular behavior. Of course, this model, along with all the other models and all the new capabilities in Marc, are fully supported by the MenCat product. In 2013, we also introduced the Marlow model. The Marlow model is a simplified material model for rubber behavior. It's nice because you can take the data from an experiment and directly go to the model. In 2013, we could take information from a uniaxial test or a biaxial test. We've now entered the capability to go using a pure shear test. But the more important thing was we added smoothing, because we didn't quite recognize that people would give us experimental data that wasn't very clean. And so one would have bumpy experimental data. What this effectively meant was that every time there was this reduction, we had strain softening, and that resulted in instabilities in the model and poor convergence. So now you can take your experimental data and one simply asks for smoothing of the data, and then you will get much better analysis behavior in your results. Moving on to contact, we introduced again in 2013 an improved way of dealing with interference fits when you had a large amount of interference. We continued this on with what we call the initial gap option, some other folks call the clearance option. it allows you to basically either deal with glued contact or small deformation sliding or large deformation sliding and large rotations, where there's an initial, either by design, imperfection in the model where there's a gap, or perhaps you did some geometric change to your model. So what we're looking at is we're looking at something that is this assembly. There actually are two different, a rigid surface and then a shell surface. So looking straight on, you see this gap. It's possible that the gap doesn't really exist if you include the shell thickness, but perhaps the gap does exist, or perhaps at a later time you want to change the thickness of this intermediate sheet or shell without remodeling the whole structure. So you could change the thickness, you could reduce the thickness, generating a clearance, and we will still, if you say include that clearance, we will use that in the simulation, and it will be as if the bodies are truly in contact with one another. And we can do this as well for large rotation type problems. Here's a model. It has initially a large gap. Of course, that's much larger than the gap clearance or the default contact clearance. And you can effectively rotate these two sheets, and you see that the initial gap tolerance is maintained. And here are some other examples. This one is done with segment-to-segment contact. A pressure is applied on the bottom sheet, and it appears as if it is continuously in contact. So it's a very user-friendly capability. It can be done with either lower order elements and higher order elements. It can be done with node-to-segment contact, and it can be used with segment-to-segment contact. Finally, the last thing I want to talk about is an option called trimming. We have reintroduced this capability. What it allows you to do is to have a load case where we say that our rigid surfaces are used to remove material, and then we use the global adaptive meshing capability to mesh the area and remove the material and generate a fine mesh. So here we used 3 trimming load cases to trim out the letters MSC from this particular model. So before I go to the demonstration, really the summary is we're really worked hard to make things easier, easier meshing, easier representation of the physical model. The one-button meshing is great because it allows you to be much more effective in generating your meshes. I know a lot of users used our complementary product, either SimX or Patran, to generate meshes and then introduce them into Mentat. There's a little less need to do that today than there was before. It allows you to effectively easily mesh the object. It allows you to take that mesh of multiple parts in this type of assembly. If we capture the names of the parts from the CAD, we can use those names as well. Or you can effectively say detect the mesh bodies, and that helps you generate your easy contact. The model tree can also be used to simplify the analysis. And of course, all this can be done, both the setup time of the model and the computational time of the model is much faster with the 2013.1 release. So I'm going to quickly bring up Mentat so you can see it live. And I've already changed a little bit some of the settings associated with MenPath in terms of the graphics colors. But we'll just try to open up that model that existed before. And I believe that's this model here. And let's fill the model. So that was my original model. As it would come in, this would basically be looking at my browser tree in this configuration. I'm afraid to say that I have a laptop machine, so the spacing may look a little narrow to you. I can, of course, expand all the folders, and we now see the model tree representing all the entities that existed in this particular model. But most likely, I don't really do that, so I usually collapse all the folders and then just look at something like my contact bodies. And again, I can see what's going on here. I can use these buttons to indicate whether or not I really want to visualize a particular contact body, or I can basically say, let's look at the gasket, and let's look at the properties of the gasket, and this is the gasket body, and it would bring up the menu that would indicate that I could change things or do whatever I want. Of course, if I had, as I say, a dual screen display, I could move this off somewhere else so as not to crowd up my menu. I can basically easily say identify the bodies, and again, I don't need to go up to view and then identify and select a contact. I can do all that automatically. And so it's just a nicer, easier way to be able to visualize and to jump from menu to menu to grab information. Of course, all these menus, if you're still used to that mode, those menus still exist. If one would be in the dynamic menu mode and you wanted to look at your material properties, you would do the same thing as you did before, and you would bring up the pop-up menu now to get your material models defined. Okay, well that's interesting, but let's look at something live. So we'll basically we'll go back into the navigator mode, and we'll open up. We'll import, and now we'll import a Parasolid model, and we'll bring up that model that we saw before. It's basically this engine model, and let's see. I hope I have my selection set correctly, and so that's the wireframe representation of this engine. So let's go and generate a finite element mesh. So we'll compute an element size, and we have to select the particular body that we want. It computed the element size, 0.013, and we'll just mesh that. And it's working on the mesh. So one of the things I didn't mention, and that is if you have models with existing solid representation, meaning that you have models that have ASYS geometries in them, then what is going to happen is if you have an MUD, we're not going to be able to convert that. But if you had an MFD, so you'll have to convert your MUD into a MFD, then we will be able to read that that body, that MUD, and we will convert your ACES geometry into a Parasolid geometry. And if you have an ACES license, then what we will do is we will provide you on a one-for-one basis a Parasolid license. And if you don't have a ACES license, then you will need to acquire a new Parasolid license. So this is the finite element mesh that we generated using the default contact tolerance. And you can see even on a Win32 machine, this is orders of magnitude faster than what we were able to achieve before. So I want to really summarize by saying I think that the new capabilities of Marc and MenCat 2013.1 are very powerful. They will make your life much more pleasant in terms of the time it takes to generate a model. The improvements of computational time are very effective. I should mention that if you are a master key customer, then utilizing the element assembly and the stress recovery based parallelization will draw additional tokens. If you are a seat license customer or a local area network license customer and you acquired parallelization licenses associated with domain decomposition method, this procedure will utilize those same licenses. If you are a seat customer or a local area license customer and you don't have any domain decomposition parallel multi-processor licenses, you will also need to acquire some new additional licenses. So I thank you very much for your time. MSC, of course, always appreciates your business and appreciates any feedback that you'd like to share with us. And I'd like to open it up for questions at this time. Thank you.